Okay, so hello and welcome back. So basically we were talking about this example over here, and it was example number 42 in the book, and we were in the middle of proving something. So basically we said that in our particular study we were talking about an equivalence relation, and we already showed that basically the relation was basically reflexive. So over here we said that basically therefore R is reflexive. So this part is done. Now the next part of the proof is that we need to prove that also that basically R is symmetric, meaning that in this particular situation we need to show that x comma y are u comma v. U comma v implies that basically this also belongs to R, meaning that this is also related to this for all x and y and u and v under belonging to A. And I think we talked about basically mathematical logic in the previous video. So whenever you have an implication, you have to assume something, meaning that you have to assume that something is true, and then based on that prove that something else is true, right? So that basically means that and in proving things, it's absolutely important to know what it is that you want to prove. Meaning that if you just keep writing, algebra is, the good thing about algebra is that you can basically keep writing algebra and play with algebra in any direction that you want, right? That's the good thing about algebra. It gives you a whole lot of freedom. You can do whatever you want to do with algebra in any direction that you want. You can go with algebra. But then the problem is that then you could end up anywhere, and that wouldn't make any sense, of course. Algebra is basically the kind of tool that you can use in order to, for example, prove that some relationship exists between a couple of variables. And so if you don't really have a very clear idea of what it is that you want to prove, you will end up just playing with algebra, and then you will never actually be able to prove whatever it is you want to prove. And one more thing about proofs is that it doesn't really matter whether you're using algebra or logic or whatever, deduction or induction or whatever it is that you're using in order to prove something. The tool is not important. The important thing is that you need to know what it is that you want to prove, meaning that you need to write down that we want to prove that this is the case, right? And of course you already know that your statement has to be completely clear, unambiguous. There has to be no problem with the statement. And then once that is the case, then you will automatically find that the right way, whether it be algebra or logic or deduction or induction or whatever else it might be, you will automatically find the right tool in order to prove whatever it is you want to prove. Or you will realize that, for example, there is something missing from your mathematics, meaning that there is some tool that you need to have in order to prove this, and that tool, you don't know it or you don't have it, and then you have to go and get it, meaning that you have to go and learn a new concept or something like that. And then of course you will be able to solve the problem, meaning that in having this approach, basically there is only 3 cases, but confusion cannot be there. Confusion is the worst thing that could ever happen to a person, of course, especially when it comes to mathematics. Case 1 would be that the statement that you want to prove you will prove that it is true. Case 2 is that you will prove that the statement that you want to prove is false. And case 3 is that you will find out that you cannot prove the statement. I mean, you're not able to prove the statement because of some tool that you don't have, and you will know what tool it is that you need to get in order to prove the statement, and then you will go off and get the tool that you need, and then you will come back and prove the statement if it's, of course, that important. Otherwise, of course, you can if it's not that important, of course, you can let it go, and then again it will come up in your exercises, and then you will either be able to solve it or not, but that's another story. So that's about proofs. So so in this particular situation, we need to show that basically that this implies this, right? So whenever you want to show that something implies something else, it's always again in the same story that we had before. We have some P, which basically we have some PQ statement. If P, then Q, and then this becomes you can think of this as P, you can think of this as Q. So this means that P implies Q, right? And whenever you have a PQ statement or a one-way implication or a simple implication, you have to basically, and the reason why you have to do this is, of course, a long story. We would need to talk about that elsewhere, not, for example, somewhere related to mathematical reasoning and logic. But long story short, whenever you have an implication like P implies Q, you have to assume that P is true, and then based on that, basically based on that, prove that Q is true. If that's the case, then that means that the statement is true. Otherwise, the statement is false, meaning that assuming that P is true, if you prove that Q is false, then the statement becomes false, right? So basically that's the whole story here. Now you can write your assumption over here, and I'm basically spending so much time on these for example, as you can see, I have spent already above one hour on one single example here. But then if you can learn mathematics properly this way, through 1, 2, 3, 4 examples, then basically my purpose and basically my purpose of being there has been fulfilled. That's my purpose of existence in mathematics. I'm not concerned about the exams and that sort of thing, and the academic part of the academic aspect of mathematics. What I care about is the understanding of mathematics, and then the applications of mathematics. That's what I mainly care about. And then based on that, I have to always change my ways in order to find the right language in order to basically get the point across. So now, so since we want to prove this, so let's assume that basically that P is true, right? So we will assume that P is true. That is we will assume that basically we will assume that x comma y is related to u comma v is true. Now, this business of true and false is a little bit tricky, and so if you use a clear language in order to write down your statements, then you will not make logical mistakes. Otherwise, if the language that you use even while you're doing mathematics with yourself, if your language is not clear, you will make logical mistakes, and of course that's not really very nice. So basically we have assumed that this statement is true. So since this statement is true, I can now assume that basically, since basically we said that over here, that that basically x comma y is related to u comma v if and only if x times v is equal to y times u. So basically then that basically means that this implies this. That means that if this is true, then it's automatically implied that this relationship exists between x and v and y and u, right? So therefore I can write over here, this implies that basically x times v is equal to y times u, right? X times v is equal to y times u. And now, of course, you need to have as I mentioned before, you need to have a very clear idea of what you want to prove. You want to prove this, right? You want to prove that this statement is true. Or it's even better to write this way. It's even better to write it this way, meaning that I can assume that P is true. That is, we will assume that basically that this is true. And I can say we want to prove that basically this statement, which is Q is true, right? And that is basically to prove that basically this statement u comma v is related to x comma y is true, right? So now I know what I can assume. I know what I need to prove. Now, if I want to prove this, so now let me go back a step, and we will get there, of course. So I can call this, for example, number 1, and I can call this number 2, right? Now, since this is the assumption that I've made that this is true, so then I can say that basically 1 implies that basically based on this statement up here, basically this statement implies this one. So x times v is equal to y times u. So therefore this implies that x times v is equal to y times u, right? Now this here is the important part. The important part is that I want to prove that this is true. So how can I prove that this is true? So if any element is related to any other element under R, it has to basically satisfy this condition. And this condition is is an if and only if situation, meaning that basically this part implies this part, and this part also implies this part. So that means that basically if I keep this condition in my mind, I can either start from this side and get to this side, or I can start from this side and get to this side. Meaning that since I want to prove that basically that this is the case, if I can show that basically u times y is equal to v times x, right? If I can show that u times y is equal to x times x, that automatically means that this belongs to, that this relationship exists, or this relation exists, right? Based on what you can see here. So if this is the case, then this relation exists. And what is this algebraic relationship? It says that x times v is equal to y times u, right? And sometimes the order is also important, meaning that, for example, I don't know, suppose that you're working on some set where there is, for example, some binary operation or something like that, where the binary operation is not commutative. Then in that case, for example, the order is important. But in this case, the order is not important at all, because you're multiplying in the set of positive integers. So automatically, basically, integers are closed under multiplication. So and that basically means that, and meaning that basically multiplication is commutative in the set of positive integers, so the order is not important here, right? So so that means that basically, if I want to show something like this is the case, then if I show something like this, the part on the right, then I can from that I can conclude that the part on the left is true, right? Okay, so basically, since I want to prove this, therefore we need, and I write this in brackets, we need to prove that basically u times y is equal to v times x, right? If I can show this, then from that I can conclude that this is true, and that's basically what I want to prove. And so how can I prove this? The only way that I can prove anything really is basically from my assumption. And my assumption was that basically that this is the case, and that implies basically this thing over here. And over here you can see that I have written x times v is equal to y times u, right? So this basically I can, of course you can already see that they are exactly the same basically algebraic expressions, but I can write this the other way around, meaning that I can write that basically this is equal to u times y is equal to v times x. So you can move this, and basically the right hand side to the left hand side to the right hand side. That you can do, of course. That is in algebra allowed. And then of course you can, instead of y times u, you can times u times y. Of course, in this particular case, sometimes you're not supposed to change the order of things. Sometimes based on the situation it's not possible really, but in this case it's not a problem. And instead of x times v, I can write v times x, right? So this automatically, so based on the condition that we have here, this automatically implies that basically I have basically two ordered pairs. That basically means that I had two ordered pairs, and those ordered pairs were related under R, right? So that means that then this u is taken from the first pair, the x is taken from the second pair, and so based on what we had up there, I can write this as u, and then leave this empty and write the R over here, and then leave this side empty, and then I can write my my Y over here, right? So U times Y is equal to V times X. Then I have to write my V over here, and the X I have to write it over here, and this order and the way that I write this is explicitly based on what I can see here, right? So there is no mystery about that or anything complicated about that. It's just based on this statement that I can see here, meaning that you can use different variables, different variable names, but whatever variable name that you choose, it has to basically be based on this template, if I may call it a template. So so then I wanted to, so then we wanted to prove 2, meaning that we wanted to prove that this is the case. And as you can see, u comma v is related to x comma y, and that's basically what we wanted to prove. So this is which is 2, or what we wanted to prove. We wanted to prove, right? So that's basically that. And so now you have to, still your work is not done. You have to basically, I mean, if I leave this over here like this, nobody knows why I did all of these things. That wouldn't make any sense. You have to come to some conclusion and tell people why you did all of these things, right? So basically now everything that you have written here, we made an assumption that P is true. So we made this assumption that this P is true, and then we came to the conclusion that Q is true, right? So we wanted to do exactly this, and we made the conclusion that P is true, and P we took as basically this statement, which is basically this thing over here. And then through logic, we came to the conclusion that Q is true. So you can say that therefore P implies Q is true, right? You can say therefore P implies Q, or you can say P implies Q is true. Both are correct. And since P implies Q is true, then R is basically symmetric, right? And therefore R is symmetric. So this is the right way of proving something. And as you can see, there is nothing mysterious about a mathematical proof. There is nothing intimidating about a mathematical proof. If you can just simply take one step after the other, logical steps one after the other, there is really nothing complicated about a mathematical proof. And a mathematical proof of this caliber is probably the most, not the most, but one of the most, basically one of the most complicated things that could ever happen in a course related to basic mathematics all the way up to class 12, right? So as you can see, it's very simple, really simple. If you know what it is that you can assume, what it is that you want to prove, and you can do that. And I mean, throughout this whole proof, I didn't look at any solutions. I had not read anything about this solution before, although I had read this chapter, for example, once before, many months ago. So I couldn't remember any of those things that I read before. But as you can see, very simply, if you go one step at a time, you can prove anything that comes your way. So it's very simple, really. Okay, so the next part is to show that basically R is transitive, right? So now basically, now we want to show that we also need to show that R is transitive. And of course, in case you're wondering why, because we wanted to show that R is an equivalence relation, so you have to show that it's reflexive, symmetric, and transitive, right? And basically the general way of showing that a relation is transitive is that basically we need to show that basically generally we need to show that basically A comma B belonging to R and basically B comma C belonging to R implies that A comma C belongs to R for all basically A, B, and C belonging to A. Now A is the set that you're working on. A, B, C are three members of that set, and basically A comma B, B comma C are two ordered pairs that you have gotten as a result of basically the Cartesian product of the set A with itself. And so then the Cartesian product, you have taken some subset of the Cartesian product that has become R, and now this belongs to R, this also belongs to R. And so if this implies that if these two belonging to R implies that this also belongs to R, then that basically means that R is transitive, right? This is the general way of showing that some general relation on some arbitrary relation R on an arbitrary set A is transitive. Now you need to, of course, make some changes to this condition so that it works for you in this particular case. And the reason you need to do that is that, of course, now you're dealing with the set that you're working with contains elements that are not in the form of ABC, they are in the form of ordered pairs, of course. So basically then you can say that in this particular case, basically we need to show that so here basically the case is like this. So you have basically, we can take x comma y, you can take anything, like for example x comma y, and for example y comma z, and then let me write it down. So in this particular case we need to show that basically now if I want to show that something belongs to R, that means that this element is related to this element under R, right? That's basically when I write basically A comma B belongs to R, that means that A is related to B under R. That's the meaning of this. Now this notation is much easier when it comes to, for example, a single elements like, for example, A and B. So there is no problem with this. But when it comes to ordered pairs, then this notation is not easy to work with anymore, meaning that you would have to write A comma B, and for example B comma C, for example, that for example belongs to R or something like that. This notation. Instead of this, you could write, for example, A comma B is related to, for example, B comma C. This is easier. So so what that means is that so what this means is that then we need to show that basically let me take a look at this. Okay, so over here you can see that basically you can see that what this part means is that some element of A is related to some other element of A, right? So when I write, for example, A comma B belongs to R, that means that some element of A is related to some other element of A. And moreover, another, basically this same element of A, B, which is B in this case, is again related to some other element of A, which is C in this case. And this basically implies that basically this element of A is related to this element of A comma C belongs to R, right? So if you think about this way, then you will be able to write the same condition for this part, and meaning that here I need to show that some element of A, take it for example X comma Y, is related to some other element of A. Let's take it for example Z comma R, for example, right? Z comma R. So these two are related, and they have nothing to do with one another whatsoever. This is X comma Y, this is Z comma R, right? And another two elements of A are also related, and these two elements happen to be the same, meaning that Z comma R is also related to, for example, A comma B, for example, right? So these two are happen to be the same. These two are related. These two are related. So we need to show that we need to show that this basically implies that basically X comma Y is related to this element over here, right? So we need to show this. So that's basically how you can simplify things for yourself, so that you can write the right condition for your situation. Now this is again some proof that you need to do, right? And it's very simple, meaning that this is basically this is the assumption that you can make. This part over here, this whole part over here, this is the assumption that you can make, and this is what you need to prove, right? So now you know what you can assume, you know what you can prove, and you know basically the rule that you want to work with. The rule is over here, right? So I take a screenshot over here so that I can copy the same thing. And the rule that you work with is basically x comma y r is related to u comma v if and only if and only if basically x times v is equal to x times v is equal to y times u. So this is the rule that you can work with. So it's now simple. Anybody can prove this. It's very, very simple. So what you need to do is that first you need to write down your assumptions. In this particular case, use algebra in order to show that basically this is the case. But before you start with proving, you need to know what you want to prove in terms of algebra. And so what that means is that basically if this is supposed to be the case, based on this rule, x times b has to be equal to y times a. If you can show this through algebra, then that automatically means that this is true, right? And you need to pay attention to the sentences that I use. Otherwise, if I want to write down all of these sentences, it would take a century to finish this. So through my proof, I will be trying to come up with this condition. If this condition is shown to be true, then I can conclude that this is the case, and that's basically what I want to prove, and this is basically what I can assume. So I can, for example, call this 1, I can call this 2 for the sake of simplicity, and basically I can say that basically 1 implies that, based on this rule, this implies that x times r is equal to y times z. And by the same logic, 2 implies that basically z times b is equal to r times a, right? And you want to show that this is the case. X times b is equal to y times a. So that basically means that you want to, from these two equations, you essentially want to get rid of r and z. You can see that there is no r or z in this expression or in this equation, but r and z are present here, right? So what you can do is that so in order so basically you need to use these two equations in order to come up with this equation, right? So what I can do is that I can simply multiply this side of this equation, multiply these two equations together, and I will get basically x times r times z times b is equal to y times z times r times a. And then z and z you can cancel out, r and r you can cancel out. R and r you can cancel out. And so you will have x times b is equal to y times a. And that is basically what you wanted to prove, right? Another way that you can solve the same problem is that you can write these equations in terms of r and z, and then basically substitute this one in that one, that one in that one, and so on and so forth in order to come up with a solution. But I suppose that this is that algebraically this is the right way of, I mean, this operation that I have done over here is most probably allowed, although I've never seen actually, I've never actually seen anybody multiplying equations together. I have to basically we will have to investigate that later, but that's not a problem. The important thing here is that basically you have these two equations over here, and using these two equations you want to prove that this is the case, and that you can do on your own using whatever basically method that you might using whatever method that might suit you, and essentially you will be able to do that. So, but then it will take a little bit of algebra in order to come up with the solution if I don't basically use this. I'm not really sure if this is not allowed. I'm not really sure, but this is basically the way that you can prove this. So that basically, suppose that, for example, now suppose that I'm assuming that basically the way that I have done algebra over here is algebraic in algebra allowed. There is no problem with that, and so I have come up with basically this result over here, and so basically then that basically this implies that basically so again, based on the rule that I have here, I can rewrite my ordered pairs, meaning that x times b, I can write my x over here, and I can write basically my b over there, and then I can write my y over here and my a over here. That means that x comma y is related to a comma b, right? So then basically we have assumed that, so we have basically made this assumption. What we have done is that you have to actually write this down, otherwise people might be confused. They don't know why you did all of these things. And so you can write therefore x comma y is related to z comma r, and z comma r is related to, for example, a comma b, implies that this is the case, that x comma y is related to basically a comma b, and therefore basically r is transitive, right? So therefore r is transitive. So that's basically that. So now what we have shown is that basically r was reflexive, it was symmetric, it was transitive, and therefore you can say that r is an equivalence relation, right? Now so let me take a look at the solution. Okay, so the solution is actually in the book. The solution is very, very short, and but then about this part that we had some problem with. So in order to solve this part, let me show you basically how basically you can solve this part as well, because I wanted to get rid of the confusion that we had here. So basically you have these two equations, and you want to show that using these two equations, you want to show that this is the case, right? So you can start with, for example, number 1, meaning that you can write x times r is equal to y times z. You already know that this is true. Now you can see that on this side of the equation, I need to have x and b, right? So I keep my x and r, and since I want to keep my x, so I don't have to do anything about the x, but I want to get a b, so I multiply by b, and I want to get rid of my r, so I divide by r. So that means that the same thing, I have multiplied by b by r. And so of course I have to do the same thing on the other side as well, y times z times b divided by r. Now these two will be cancelled out. I'm left with x times b is equal to yz times b by r, right? Now on this side, I need an a, and I need to get rid of this b, I need to get rid of this r, I need to get rid of this z. So how do I do that? So you need to basically, for example, you can use this equation here, and this equation implies that z is equal to ra divided by b, right? So instead of z, if over here, if I write x times b is equal to y, and z, I can write it as ra divided by b, and then I have another b divided by r over here. Then r and r you can cancel out, b and b you can cancel out. X times b is equal to y times a, and that's basically what we wanted to show here. So that's how you can solve this problem about multiplying the equations together. I'm not really sure if it's actually allowed in algebra, really. You're not supposed to do, whatever comes to your mind, you're not supposed to do in algebra, because well, in some situations it might be okay, but then you have to think about the consequences of what you do in algebra. Not everything is allowed in algebra, because you might do something unknowing, and unknowingly you might actually break something. It's not, what I did over here, of course, was not safe. But then this is actually the right way of, this is one valid way that I'm 100% sure about to solve this problem. So this was question number 42. I hope that you learned. I hope that you learned a little something in this example. I'm essentially picking these examples, and then through these examples, what I'm doing is that I'm basically trying to make the concepts understood. That's what I'm doing here. And for example, this single example, it's just a couple of lines in the book, but it took us 2 hours to solve. It was of course worth it, but then well, this approach of course sometimes takes a lot of time, but then, well, mathematics sometimes does take a lot of time, so you have that's a fact about mathematics. You cannot basically get around that. Sometimes you can take care of things pretty easily. Sometimes you have to spend more time on some other things. So it's just, but the whole thing will sort itself out, of course. Okay, I'm going to end this video here. In the next video, we will talk about example number 43. I'll see you in the next video, and thank you.